Let's discuss question number 38 from test 1. Let's read the question. A fan that consumes 20 watts of electric power discharges air from a ventilated room at a rate of 0.25 kg per second, and the maximum air outlet velocity is asked. So this is a question from thermodynamics. Okay, so let's model it. You have a fan here, a ventilated room, which basically takes the air. Which basically takes the air and gives out with, or provides it the kinetic energy, forces the air to the outside. So you have a fan here. So what we do is we consider this as our control volume, okay, where all the action is happening. Okay, so now this is our inlet section, this is outlet section. Okay, and let's apply first law of thermodynamics. So I'm just applying per unit mass flow rate, or let's write down for per unit mass flow rate. So at the inlet section, the input energy associated with the flow is this enthalpy part plus your kinetic term plus your potential term plus whatever the heat added. So I'm just writing in a general sense, plus the outlet energy of the fluid. So again, the enthalpy term, the kinetic energy term, the potential term, plus work done by the fluid. Okay, so this is your general equation, or in terms of, so this is per unit mass flow rate. So if you add the mass flow rate, so it will be something like this. So this is again heat added per mass flow rate. So again the m dot plus v2 square by 2g plus g z2 plus work done plus, or the total work done. Okay, so let's write total heat added and total work done. Okay, so now let's see what is given. 200 watt of electric power. So work is done on the system. So work is basically done on the system. Now in this expression, work is done by the system or by the air. So minus 200 watt. Okay, and how do you find out enthalpies? Now because the data is not given, how it's air can be assumed as the change in enthalpy of the air is related to the change in temperature, like this, but the data is not given, so we assume that it's isothermal. The process is isothermal, no change in temperature. This is for any ideal gas, and air I can assume it to be ideal gas, so no change in temperature. That is one of the assumptions, because the data is not given. Otherwise, if you would have given the change in temperature, we can just consider enthalpy change. So we assume that there is no change in enthalpy. The potentials are all same, because a fan, the inlet and outlet is same, and inlet velocity is zero, because the fan work, it forces out and it gives some velocity. So under these conditions, let's substitute, and the heat added is 0, there's no heat added. So all this condition would lead to the fact that left hand side it's 0, right hand side it's mass, H2 is 0, H1 and H2 cancel out. Velocity, you have outlet velocity v2 square by 2, and work done, this is minus 20. So now outlet velocity is 20 into 2 by mass flow rate, and then the square root. So 20 watt into 2 by mass flow rate is given as 0.25. So this comes out to be 40 by 0.25, and when you use a calculator, so this is root 160 basically, okay, into 4. So when you use a calculator, this comes out to be 12.65 meters per second. So the option is D. So this is just a simple application of first law of thermodynamics. So understand how we have neglected each of the terms. Okay, so thank you.